Hello, friend, and welcome back to Science for Sleep, a quiet place where curiosity drifts slowly and the universe feels soft enough to rest inside for a while. Tonight, we'll explore the origins of the Milky Way, not through urgency or diagrams or sharp explanations, but through a gentle wandering into how something so enormous and ancient came to be. Even the vast galaxy that holds our little world began as something small and shimmering, gathering itself together over unthinkably long stretches of time, long before stars like our sun ever opened their eyes, long before any shape we would recognize existed. The early universe was filled with delicate fluctuations of gas and dark matter. Astronomers believe the Milky Way began taking form around 13.5 billion years ago, when those faint variations allowed gravity to pull material into slowly tightening clumps. Within these early gatherings, the first stars ignited, lighting pockets of hydrogen that had been drifting quietly since the universe's beginning. Over time, these clusters merged with one another, creating larger and larger structures that hinted at the spiral we now see stretching across our night sky. As we settle into this quiet story, you might picture these early clouds as soft, pale currents drifting in a universe still finding its rhythm. Nothing rushed and nothing hurried. Gravity moved like a slow breath, drawing material inward, letting it settle, and shaping it gradually into something that would one day become home to billions upon billions of stars. The Milky Way's birth wasn't a single moment, but a long unfolding, a gentle gathering of light that would eventually host our entire cosmic neighborhood. If you enjoy these quiet journeys, I invite you to subscribe, and if you feel comfortable, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. For now, you can let the pace slow even further, allowing your thoughts to loosen as we drift deeper into the galaxy's earliest memories. And as the shapes of those first star clusters fade into a soft glow, we can let ourselves follow them, unhurried, into the deeper layers of how the Milky Way assembled its structure piece by piece over billions of peaceful years. I'm glad you're here. There's a calmness in imagining the universe at a time when almost nothing had yet taken shape, when light itself was still learning where to gather and how to shine. In that quiet era, long before the familiar spiral of the Milky Way unfurled its arms, the cosmos was filled with gentle gradients of temperature and density. These faint variations, left over from the early expansion of the universe, created places where gravity tugged just a little more firmly, inviting matter to drift inward. With each small pull, the earliest ingredients of our galaxy began settling into patterns that would one day become recognizable, though no observer existed to watch them form. Astronomers think the very first pieces of the Milky Way began as loosely connected halos of dark matter, structures that shaped where ordinary gas could collect. Dark matter doesn't shine or interact with light, yet its gravitational pull guided enormous clouds of hydrogen into regions where they could cool and compress. As these clouds condensed, stars began to ignite inside them, marking the earliest chapters of galactic formation. These newborn stars were made almost entirely of hydrogen and helium, because heavier elements had not yet been forged. Over time, as some of those early stars lived and faded, they enriched their surroundings with new elements, gradually allowing the galaxy to build stars more similar to those we see today. If you picture this moment, it might feel like watching soft currents drift through a vast stillness. Hydrogen clouds flowed into those invisible dark matter wells, as though guided by gentle currents underwater, settling deeper each time gravity pulled them inward. The universe had far more emptiness than structure, yet within that emptiness, the seeds of an entire galaxy were quietly drawing together. Nothing about the process was sudden. Even when stars first erupted into light, they did so in clusters spread across enormous distances, each one a small lantern in a sea of silence. Researchers studying this early stage use observations of distant galaxies to understand what our own might have looked like in its youth. Because light takes time to reach us, telescopes can effectively look backward into eras when galaxies were still faint and irregular. These young galaxies show us how uneven and clumpy the early universe truly was, with no grand spirals, no smooth disks, and no sweeping lanes of starlight. Instead, they appear as soft knots of illumination, merging and separating over billions of years. Our Milky Way likely resembled these small, lumpy collections of stars at first, growing only through gradual gathering and the merger of many such pieces. And so, the earliest form of our galaxy drifted through cosmic time as a quiet, uneven glow, a collection of star clusters and gas clouds slowly being drawn into a shared center. Each gentle movement added to its weight. Each new star contributed a faint shimmer, and each merger nudged it slightly closer to the shape it would someday hold. All of it unfolded with a patience far beyond anything we experience here, inviting us to imagine the calm, sprawling beginnings of the place that would one day cradle our own tiny world. In the deep quiet of those early epochs, the young Milky Way was far from the graceful spiral we see painted across long exposure photographs of the night sky. Instead, it drifted as an irregular swell of glowing knots, each one a cluster of early stars forming within cooling clouds of gas. These clusters lived within a slowly tightening envelope of dark matter, gently guided by gravitational currents that shaped the galaxy, without ever revealing themselves to light. Everything about this time felt unsettled yet unhurried, as though the cosmos were slowly learning how to gather itself into something coherent. One of the remarkable scientific insights about this era comes from simulations that show how early galaxies grew by drawing in streams of cold gas from their surroundings. These rivers of hydrogen flowed inward along the filaments of the cosmic web, supplying the raw material for new stars to take shape. As these inflowing streams reached the galaxy's center, they began contributing to a small but steadily growing bulge, one of the first true structural features of the Milky Way. Astronomers believe that this central bulge formed before the spiral arms existed, providing the first hint of a stable, long-term core. The stars in this region are incredibly old, some among the oldest in the entire galaxy, preserving chemical signatures that trace back to the universe's earliest generations. If you let your thoughts follow these ancient flows for a moment, you might picture them as soft, transparent currents, drifting through a space so vast that even light seemed to wander. Each stream carried with it the quiet potential for new starlight, and each gentle convergence added mass to the young galaxy. Nothing here was frantic. The hydrogen clouds had no urgency, no need to hurry toward their destinations. Gravity drew them inward with the slowness of a drifting tide, shaping what would eventually become the foundations of our galactic home. Scientists studying the oldest stars near the galactic center have found that many contain very few heavy elements, confirming their birth in the early cosmos before repeated cycles of star formation enrich the galaxy. Their chemical fingerprints act like soft echoes of an environment far simpler than the one we know now, a time before the Milky Way had layers of starlight, dust lanes, or spiraling arms. These ancient stars move in orbits that are more chaotic than those of younger stars, suggesting they formed during a period when the galaxy had not yet settled into a smooth rotational pattern. Through their motions and chemistry, astronomers reconstruct the quiet turbulence of that early epoch, reading the motions of stars the way one might watch grains of sand drifting in a shallow tide pool. As these early structures continued to merge and brighten, the future Milky Way gathered a little more weight and a little more stability. The central bulge thickened, star clusters settled deeper into orbit, and the once loose shape of the galaxy began to take on the faint suggestion of an organized form. Everything moved with cosmic patience, as though the galaxy was stretching toward a shape it would not fully achieve for billions of years. In those slow shifts, the groundwork for the Milky Way's future beauty was laid, waiting quietly for the next layer of starlight to arrive. There's a quiet elegance in imagining the Milky Way during the stage when its earliest stars had already begun to shine, yet the galaxy itself still lacked the sweeping form we know today. In this calm and ancient time, the young galaxy resembled a loose, uneven sphere of starlight and cooling gas, drifting through a universe that had only recently begun to assemble its largest structures. Gravity was the gentle sculptor here, shaping motions so slow and subtle that even millions of years would appear as little more than a soft shift in direction. One of the most important processes unfolding in this era was the cooling of gas within the forming galaxy. As hydrogen clouds lost heat, they became more compact, allowing new generations of stars to form. This cooling was aided by the presence of helium and trace amounts of the earliest heavy elements, which allowed gas to radiate energy away more efficiently. At the same time, the galaxy's growing mass created a deeper gravitational well, enabling it to pull in material from farther distances. These combined effects allowed the Milky Way to gather more gas than its earliest state would ever have suggested. The young galaxy slowly transitioned from a scattered cluster of star-forming regions into a more unified, luminous structure. If you picture this development, it may feel like watching soft layers of mist being drawn toward a quiet center. Each cloud carried its own potential, drifting gently as starlight began to carve faint patterns through the darkness. The heating from newborn stars created pockets of turbulence, but even those interactions unfolded at such vast scales that they seemed more like slow ripples moving through a calm pond. Over millions of years, the distribution of gas shifted, becoming flatter and more aligned with a slowly emerging plane of rotation. Nothing forced this change. It emerged naturally from the collective motions of stars and gas, the way a group of fireflies might gradually organize their flight into a graceful pattern without any specific intent. Researchers studying these early motions have found that the transition toward a disk began when the inflowing gas carried angular momentum, an intrinsic rotation built into the galaxy's environment. As this rotating material accumulated, It caused the galaxy to spin more coherently, smoothing out chaotic orbits into more circular ones. This process marked a turning point. Instead of resembling a lumpy sphere, the Milky Way began flattening into the primitive disk that would later host its spiral arms. Evidence of this early rotation can be traced in the orbits of metal-poor stars that still move in thick inclined patterns, relics of a time when the galaxy was settling into a new shape. Their motions preserve a record of those slow, formative years, allowing astronomers to reconstruct how the early disk first emerged. Gradually, the galaxy became a place where older stars hovered in a thick, faintly rounded halo, while newer stars formed within a developing, rotating disk closer to the center. The early halo remained a soft reminder of the Milky Way's chaotic youth, while the disk represented the beginning of a more organized and balanced structure. Through these shifts, the galaxy continued gathering mass and light, preparing for the moment when it would blossom into the familiar spiral form we recognize across dark skies on clear, quiet nights. All of it unfolded with vast patience, allowing every motion to settle before the next one began, giving the galaxy time to grow into its own gentle rhythm. There's something soothing about imagining the Milky Way at the moment, when its early disk had just begun to settle, like a delicate sheet of starlight slowly unfurling across cosmic darkness. The galaxy was no longer a shapeless sphere of uneven glow. It had started to flatten, guided by the natural rotation carried in from the streams of gas drifting toward it from the larger universe. This young disk was thick and somewhat clumpy, not yet the elegant, thin structure we see today, but it held the first hints of order within the vast stillness. During this period, new stars formed rapidly within the cooling gas of the disk. These early disk stars differed from the ancient halo stars that orbited far above and below the galactic plane. They contained slightly more heavy elements, evidence that earlier generations of stars had already lived and faded, enriching the gas with elements like carbon, oxygen, and small traces of iron. Astronomers observe these chemical signatures today to piece together the timeline of the Milky Way's growth. The patterns reveal that the inner regions of the disk formed quickly, creating bright, long-lived stars whose motions help define the early shape of the galaxy. As more material settled into rotation, the disk thickened and gained structure, gradually becoming a more stable environment for star formation. Letting your thoughts drift through this scene, you might picture rivers of gas spiraling inward, glowing faintly as newborn stars illuminated the surrounding dust. Each cloud collapsed slowly under its own weight, forming a cluster whose starlight spread like a soft haze through the early galaxy. The disk wasn't smooth then. It was filled with knots of gas, lanes of cooling material, and patches where starlight and shadow blended into gradients. Yet even within that unevenness, you can imagine the quiet predictability of rotation, an ancient, steady motion that gently encouraged the galaxy to smooth itself over time. The more it rotated, the more its stars and gas aligned with the disk's growing plane, like pebbles sinking into the tranquil bed of a broad river. Astronomers studying nearby stars have uncovered evidence that the early Milky Way disk grew in waves rather than all at once. Chemical gradients across the disk show that the inner regions form stars faster and earlier than the outer portions, suggesting a kind of inside-out growth. Meanwhile, traces of older stellar populations reveal that the thick disk, an elevated, puffier layer surrounding the thin disk, contains stars with older ages and more chaotic histories. Their orbits hint at ancient interactions and early turbulence before the disk settled into a thinner, more refined structure. These findings help researchers reconstruct how the galaxy matured, one layer at a time, and how its earliest motions shaped the environment that would one day cradle solar systems like our own. Over vast stretches of time, the disk continued to expand, gathering new gas from the cosmic web and smoothing itself into a more balanced form. Each rotation contributed to its refinement, allowing the galaxy to drift closer to the graceful pattern that defines it today. In this slow unfolding, the Milky Way learned to hold both its old halo stars and its younger disk stars in quiet harmony, carrying forward the story of its creation through every orbit they traced across the darkness. The galaxy was still changing, still finding its structure, and yet it already carried within it the soft promise of the spiral form that would one day stretch across the sky like a gentle brushstroke of light. It's calming to imagine the Milky Way carrying on through these early ages, slowly gathering confidence in its shape as new layers of starlight settled into place. The galaxy had begun to rotate more smoothly now, its thick disk turning with a gentle regularity that helped guide the motions of newly forming clusters. Even though it was still far from the elegant spiral we know, the underlying rhythm of rotation was beginning to influence everything: the flows of gas, the orbits of stars, and the subtle emergence of patterns that hinted at what was to come. One of the important scientific understandings from this era involves the behavior of gas within the rotating disk. As the galaxy spun, regions of gas experienced slight compressions whenever they encountered spiral-like density waves, even before fully defined spiral arms existed. These compressions made the gas more likely to form new stars, creating pockets of brightness that slowly traced arcs across the disk. Astronomers now believe that these early density waves were among the first steps toward the development of the Milky Way's spiral structure. Meanwhile, the gas that continued to fall in from cosmic filaments brought fresh material to fuel star formation, ensuring that the disk brightened steadily over many billions of years. These combined processes began to shape a disk where star formation was no longer chaotic, but gently patterned by the galaxy's rotation. If you let these motions drift into your thoughts, you might imagine faint ripples running through a quiet lake, forming subtle curves that guide floating petals into delicate spirals. The early Milky Way felt something like this: soft, recurring shapes emerging naturally from the interplay of gravity, motion, and time. Each ripple of compressed gas birthed clusters of young blue stars, whose glow spread across the surrounding dust as though lighting the faintest outlines of future arms. Nothing about it was forceful. These patterns appeared gradually, as if the galaxy were tracing the first light sketches of a design it would refine for the rest of its life. Researchers have examined the ages and chemical compositions of stars in the thick and thin disks to infer how the galaxy changed through these early rotations. Stars in the thick disk tend to be older and richer in certain chemical elements that form during rapid bursts of star formation, suggesting that the early Milky Way experienced periods of intense stellar birth followed by quieter intervals. As the gas supply became more stable, the thin disk formed as a calmer, flatter structure, where star formation continued at a steadier rhythm. These differences allow astronomers to chart the transition from a turbulent, rapidly changing galaxy into one with more predictable and enduring patterns. Through this, the story of early spiral development becomes clearer, one of slow refinement rather than sudden transformation. Across millions of rotations, the pale arcs of star-forming regions grew more pronounced, shaping the galactic disk with soft and gradually strengthening curvature. Each new generation of stars added weight and light to the forming patterns, helping the spiral outlines become smoother and more continuous. Even though the Milky Way was still young compared to what it would one day become, the essence of its character was already forming in these early motions. The galaxy was learning how to turn, how to gather its light, and how to trace the first delicate hints of the spiral arms that would eventually stretch across deep time and distant space with such quiet beauty. There's a peacefulness in imagining the Milky Way continuing to grow through encounters with small, wandering galaxies that drifted close enough to be drawn in by its gravity. The early universe was filled with these smaller systems, many of them only loose gatherings of stars and gas, carrying their own quiet histories as they floated through cosmic space. When one of them approached the young Milky Way, their paths would gently intertwine, allowing the larger galaxy to absorb stars, gas, and even dark matter. These quiet mergers were not abrupt collisions, but rather slow, graceful interactions that unfolded across hundreds of millions of years, shaping the Milky Way with the soft patience that defines so much of cosmic evolution. Astronomers studying the halo of our galaxy have found streams of stars moving together in elongated arcs, remnants of these ancient mergers. These stellar streams act like soft signatures left behind by long-lost galaxies, preserving their shapes even after being stretched and mixed into the Milky Way's outer regions. One of the most studied examples is the Sagittarius dwarf galaxy, which is currently being tidally stripped by the Milky Way's gravity, leaving long trails of stars in its wake. Though this ongoing interaction is much more recent than the galaxy's earliest phase, it shows how past mergers would have looked, offering a living example of a process that has shaped the Milky Way for billions of years. The halo of the galaxy still carries many of these relics, allowing astronomers to reconstruct a quiet, intricate tapestry of ancient encounters. If you let your thoughts rest on this idea, you might envision faint rivers of stars drifting slowly toward the brighter glow of the Milky Way, their motions almost imperceptible on human timescales. Each small galaxy moved like a soft lantern floating across deep water, gradually drawn toward the larger luminous shape ahead. As they neared, their stars were gently pulled apart, stretched into long arcs that wrapped around the growing galaxy. Over time, these arcs faded into the halo, contributing not only light, but also clues about the Milky Way's early growth. The process was so prolonged and so gentle that even the stars being drawn away from their original homes experienced no sudden change, only a slow, quiet redirection of their paths. Research into the chemical composition of halo stars reveals further hints about these long-ago mergers. Many halo stars contain fewer heavy elements than those formed in the Milky Way's disk, suggesting they originated in smaller galaxies, where star formation was slower and less enriched. Some halo stars follow orbits that are highly inclined or even retrograde, moving opposite the galaxy's main rotation, which indicates that they were captured from foreign systems rather than born within the Milky Way. These signatures allow astronomers to identify distinct merger events, each one contributing to the galaxy's mass and shape. Through this careful study, the history of the Milky Way becomes less mysterious, revealing the many small companions that quietly gave pieces of themselves to help form the galaxy we live in today. Over time, each merger added subtle changes to the Milky Way's structure, thickening the disk, enriching the halo, and adding complexity to the galaxy's overall motion. These interactions didn't disrupt the galaxy's formation, but complemented it, adding new layers of starlight and gentle variation in the orbits of stars. Through these ancient encounters, the Milky Way developed a richer and more intricate personality, carrying forward the quiet contributions of countless smaller galaxies that drifted into its embrace. Each one became part of the larger whole, helping shape the spiral that would eventually unfurl across cosmic time with such serene beauty. It can be comforting to picture the Milky Way during the time when it was beginning to gather enough mass and motion for its future spiral arms to take clearer shape. The galaxy was no longer just a thick, unsettled disk filled with scattered clusters. Its rotation had become steadier, and the inflow of new gas created subtle gradients that encouraged star formation in certain regions more than others. Though the spiral arms had not yet fully emerged, the foundation for them was quietly building, shaped by the large-scale patterns of motion flowing through the galactic disk. One of the central scientific ideas behind spiral arm formation is the concept of density waves, regions of slightly higher density that move through the galactic disk at a different speed than the stars themselves. As gas passes through one of these waves, it slows and compresses, triggering new star formation. This effect means the arms are not solid structures, but rather patterns that persist even as individual stars move in and out of them. Astronomers observe these waves in many spiral galaxies and believe similar processes were active in the early Milky Way. These density variations mark the places where bright clusters of young stars began to emerge, creating soft, glowing arcs that hinted at the spiral form still developing. At the same time, gravitational interactions between stars and clouds helped reinforce the pattern, allowing these early arms to become more stable over billions of years. Thinking of these density waves, you might imagine them as soft bands of pressure moving through a pale sea of gas and starlight, nudging material into gentle curves. Each wave carried no abrupt force, only a quiet influence that shaped the gas into regions where its own weight could bring it together. As the wave passed, the newborn stars it left behind illuminated the path with a faint shimmer. Their glow didn't last forever. Many young, massive stars burned out quickly, but their presence helped sketch the earliest outlines of the spiral arms, like the first brushstrokes on a slowly emerging canvas. The galaxy was beginning to show hints of the symmetry and elegance we now associate with its iconic form. Astronomers studying the internal motions of stars have found that the Milky Way's rotation curve, how quickly stars orbit at different distances from the center, remains relatively flat across much of the disk. This behavior, influenced by the presence of dark matter, helps maintain the persistence of spiral patterns rather than allowing them to wind up tightly over time. Meanwhile, measurements of gas distribution reveal that certain regions of the disk are more efficient at forming new stars, a pattern consistent with density wave theory. These scientific findings give researchers insight into the quiet, rhythmic processes that shape the galaxy long before its structure became well defined. They show that even in its earliest stages, the Milky Way followed subtle rules of motion that guided the emergence of its spirals. Over countless rotations, the repeated passage of gas through these density waves created enduring arcs of light, gradually strengthening them until they resembled the graceful arms that today stretch outward from the galactic center. Each cycle added new stars and refined the pattern a little more, allowing the galaxy to settle into the shape we now recognize in long exposure images and artist renderings. Though these arms were only beginning to form, they carried the promise of the Milky Way's future beauty, revealing the quiet interplay of motion, gravity, and light that sculpted the galaxy into the gentle spiral we call home. There's a quiet wonder in imagining the Milky Way during the period when its young spiral arms were starting to feel more defined, yet still shimmered with the looseness of a galaxy discovering its form. The arms were not rigid structures, but gentle gathering places where gas and stars drifted together under the influence of subtle density waves. In these tranquil regions, bright clusters of new stars illuminated the dust around them, forming glowing patches that slowly traced the curves of the developing spiral. The galaxy was settling into a new elegance, learning to guide its material along soft pathways that would eventually become familiar outlines stretching across the sky. One of the key scientific insights from this era involves the ongoing enrichment of the galaxy's interstellar medium. As new generations of stars lived and faded, they returned heavier elements to the surrounding gas through gentle stellar winds and supernova remnants. These enriched materials allowed later stars to form with more diverse compositions, including the elements needed for rocky planets to emerge. Astronomers observed this gradual buildup of heavy elements, called metallicity, as a signature of the galaxy's age and growth. Stars closer to the center tend to have higher metallicity, reflecting more cycles of formation and enrichment, while those farther out often preserve the simpler chemical makeup of earlier times. This gradient helps researchers map the timeline of the Milky Way's evolution, showing how enrichment spread outward like a soft ripple over billions of years. If you follow this enrichment in your imagination, it might feel like watching pigments slowly mix into a wash of watercolor, the hues deepening gently as each new layer settles in. The earliest stars produced almost no heavy elements, but with each generation, the galaxy's palette grew more varied. Gas clouds enriched by previous stars formed new clusters whose compositions reflected the quiet history of everything that came before. You could picture these clouds drifting through the spiral arms, carrying the soft glow of future possibilities. Over time, the enriched regions brightened with younger, bluer stars, while older stars lingered in the outer halo, their orbits more erratic and their chemistry simpler. Together, they created a layered mosaic of ages and elements, each star a quiet record of its moment in the Milky Way's unfolding story. Astronomers studying the motion of stars in the disk have found that the Milky Way undergoes a process called radial migration. Over long timescales, stars can move inward or outward within the disk, shifting their positions without disturbing the galaxy's overall structure. This drift occurs when stars interact with spiral arms or the central bar, gaining or losing angular momentum in a way that gently changes their orbits. Radial migration helps explain why stars with different ages and chemical compositions can appear in regions where they would not be expected based solely on where the galaxy formed them. It adds a soft complexity to the Milky Way's evolution, revealing that the disk is not a static place, but a dynamic, slowly shifting environment where stars wander over billions of years. Through all of these changes, the enrichment of the gas, the drift of stars within the disk, and the strengthening of the spiral pattern, the Milky Way was becoming increasingly cohesive. Its shape grew more refined, its motions more harmonious, and its layers more intricately linked. The galaxy was not finished growing, nor had it reached the form we see today, but its identity was gradually settling. Each quiet rotation brought new adjustments, smoothing out irregularities and deepening the spiral structure. The Milky Way continued to glow with the soft radiance of countless stars, carrying within each one a trace of the ancient processes that shaped this gentle and enduring home in the cosmos. There is something calming in imagining the Milky Way becoming more interconnected as time moved through its vast, barely noticeable flow. The galaxy was no longer a loose collection of structures, but a system where the bar, the disk, the halo, and the spiral arms were beginning to influence each other in subtle ways. These components didn't form all at once, but grew gradually, each shaped by gravity, rotation, and the continuous infall of gas drifting in from the larger cosmos. As the Milky Way matured, these relationships began to define how material moved within the galaxy, creating rhythms that would guide its evolution for billions of years. Even in this early stage of refinement, the Milky Way carried a sense of cohesion, as though each part understood how to shape and be shaped by the others. One of the central scientific insights from this period involves the role of the galactic halo, a vast region surrounding the disk that contains some of the oldest stars the Milky Way has ever formed or acquired. These halo stars orbit in highly elongated paths, revealing clues about ancient mergers and the early gravitational environment of the galaxy. The halo also holds globular clusters, dense, spherical collections of stars that formed both inside the Milky Way and in smaller galaxies that were later absorbed. Astronomers can estimate the ages of these clusters by studying the properties of their stars, finding that many date back nearly to the beginning of the galaxy itself. Their presence offers a window into the Milky Way's youth, showing how the earliest building blocks settled into a stable configuration long before the spiral disk became dominant. Letting your thoughts drift into this halo, you might picture it as a soft, faintly glowing shell surrounding the brighter disk below. Its stars move slowly across great arcs, tracing paths that have remained steady for billions of years. Some of these orbits are so inclined that they sweep high above the disk and then plunge back through it, carrying with them the quiet signatures of old galaxies that once drifted close enough to be absorbed. Others move in more circular paths, having been shaped by the Milky Way's own gravity during moments of early calm. In this wide and quiet envelope, the galaxy's history feels suspended, each orbit like a gentle brushstroke describing where the Milky Way has traveled in its long journey through cosmic time. Researchers studying the halo have identified distinct populations of stars that come from different origins. Some clusters and streams belong to the so-called Gaia Sausage Enceladus event, a major ancient merger that played a significant role in shaping the early Milky Way. Evidence for this comes from the star's chemistry and their unusual orbital motions, which differ from those formed within the galaxy's original core. Other stars in the halo appear even older, likely forming during the earliest collapse of primordial gas that preceded most of the galaxy's structure. These findings reveal that the halo is not a single population, but a layered archive, holding the quiet remnants of many galaxies that once added their stars to the Milky Way's growing mass. Over time, the interactions between the halo and the disk created subtle imprints on the galaxy's evolution. The gravitational influence of halo stars helped shape the distribution of material in the disk, while the continued arrival of small satellite galaxies occasionally stirred the Milky Way's outer regions. Despite these interactions, the overall structure of the galaxy grew more stable as it settled into long-term patterns. The bar thickened, the spiral arms strengthened their curvature, and the disk continued to expand as new material arrived. Through all of these changes, the halo remained a quiet guardian of the galaxy's past, carrying with it the lingering glow of stars born near the dawn of time. Its presence gave the Milky Way a deep and ancient foundation, upon which all later structures would unfold with graceful patience. Far from the bright center of the Milky Way, the outer regions of the galaxy unfolded in a quieter, more fragile way, shaped less by dense star formation and more by the graceful pull of gravity, working across vast distances. These outskirts were not empty, but they held fewer stars, allowing the dark lanes of gas and dust to drift with a looser rhythm. In these remote stretches, the spiral arms were softer and less defined, fading gently as they reached toward the halo. This part of the galaxy grew more slowly than the inner disk, influenced by the gradual arrival of gas from the cosmic web and by the subtle tug of nearby satellite galaxies that brushed the Milky Way's gravitational boundary. Here, the galaxy's structure felt delicate, as if still deciding where starlight should gather and where darkness should remain. One of the most meaningful scientific insights about the outer Milky Way is the presence of extended hydrogen envelopes, vast clouds of neutral hydrogen gas that stretch far beyond the visible spiral arms. Radio observations reveal that these outer regions rotate almost as quickly as the inner disk, a surprising behavior that helped astronomers realize the Milky Way must contain large amounts of unseen dark matter. Without this additional mass, the outer stars and gas would not be able to maintain their orbits at such high speeds. This flat rotation curve remains one of the foundational pieces of evidence for dark matter, showing that the galaxy's true structure extends far beyond what our eyes can see. These outer hydrogen layers also act as reservoirs of material that the spiral arms can draw upon, supplying fresh gas for star formation over billions of years. If you picture these outer regions, they might feel like soft, slow-moving tides brushing against the edge of a vast, starlit shore. The gas flows in long, thin streams that drift around the galaxy's curve, tracing patterns that are almost invisible except to instruments tuned to their faint whispers. Stars out here move with a gentler companionship, spread far apart yet still following the quiet guidance of the Milky Way's rotation. The spiral arms lose their crisp definition, dissolving into loose filaments and solitary clusters that shimmer like distant lanterns against the darkness. It's a place where the galaxy feels unhurried, where each small pocket of light seems to float in its own calm orbit. untouched by the denser activity closer to the center. Astronomers studying the outskirts have discovered another intriguing feature: the warped shape of the outer disk. Instead of lying perfectly flat, the disk bends slightly upward on one side and downward on the other, forming a subtle wave-like pattern. This warp is thought to result from gravitational interactions with nearby satellite galaxies, particularly the Large and Small Magellanic Clouds. Their combined influence may tug gently on the Milky Way's outer gas, creating a ripple that moves slowly across the disk. Observations show that this warp has persisted for a long time, silently recording the ongoing relationship between the Milky Way and its closest companions. It adds a quiet complexity to the galaxy's form, reminding us that even large, mature galaxies remain sensitive to the motions of their smaller neighbors. Over immense stretches of time, the outer disk continued to expand and shift, shaped by infalling gas, distant mergers, and the constant rotation of the galaxy. These faint regions, though far from the bright center, played an essential role in the Milky Way's evolution, providing both the material and the space for new structures to grow. As the galaxy matured, its outskirts remained a gentle boundary where the visible and the unseen met, a place where the influence of dark matter, hydrogen clouds, and faint stellar streams quietly blended. In the slow drift of these distant layers, the Milky Way carried forward its ancient rhythm, stretching its spiral form across the cosmos with a balance that felt both delicate and enduring. Light behaves differently in the center of the Milky Way, where stars gather so densely that their glow blends into a soft, uninterrupted radiance. Instead of distinct points of light, the central regions appear as a concentrated sweep of brightness, shaped by the motions of countless stars that orbit close to the heart of the galaxy. These stars move faster than those in the outer disk, responding to the deep gravitational well that sits at the Milky Way's core. Their paths create a dynamic environment full of gentle turbulence and shifting patterns, a place where the galaxy reveals the quiet strength hidden beneath its spiral arms. Over billions of years, this inner region matured from a loose gathering of early clusters into a luminous, structured hub that helps anchor the entire galaxy's rotation. One of the central scientific discoveries about this galactic core is the presence of Sagittarius A star, the Milky Way's supermassive black hole. Measuring roughly 4 million times the mass of the Sun, it sits deep within the central bulge, shaping the orbits of nearby stars through its gravitational pull. Astronomers tracked these stars for decades to confirm the black hole's existence, watching them complete elliptical paths that swing astonishingly close to the center before sweeping outward again. These orbits move so predictably that they allow researchers to calculate the mass of the black hole with remarkable precision. Despite its immense influence, Sagittarius, a star, remains quiet compared to black holes in more active galaxies, feeding only slowly on surrounding material. Its calm behavior creates an unexpectedly gentle center for a structure as vast as the Milky Way. Imagining this environment, you might picture stars drifting through a warm, golden haze, their motions smooth and unhurried despite the enormous forces guiding them. Dust clouds weave through the light, dimming some regions while revealing others, creating soft gradients that shift as the galaxy rotates. The presence of the central bar adds another layer of motion, guiding streams of gas inward in long, curved paths. These streams move like slow currents swirling toward a quiet depth, delivering the raw material for new stars to form near the core. The combination of strong gravity, dense starlight, and drifting clouds gives the central region a layered texture, almost like a cosmic hearth where light gathers and deepens before spreading outward across the disk. Scientific observations also reveal that the stars in the central bulge differ from those in the spiral arms. Many are older and richer in certain heavy elements, suggesting they formed rapidly during an early burst of star formation. The bulge is not a simple sphere, but a boxy, elongated structure shaped by the evolution of the central bar, which redistributes stars over long periods. Infrared surveys have helped astronomers map this region through the thick clouds of dust that obscure it in visible light, revealing a detailed structure with subtle twists and layers. These findings show that the bulge grew not only through early collapse and star formation, but also through the slow rearrangement of stars driven by the bar's rotation. Even the quietest parts of the galaxy's core hold evidence of long, patient changes unfolding over billions of years. Through all of these processes, the influence of the supermassive black hole, the inward flow of gas, the evolution of the bar, and the aging of the bulge, the center of the Milky Way became a steady, luminous anchor for the rest of the galaxy. Its gravity helped stabilize the spiral arms, while its star-forming regions added warmth and radiance to the inner disk. Though the outer regions grew more slowly and gently, the core carried a deep, ancient energy that shaped the galaxy's identity. In the glow of this crowded heart, the Milky Way continued to refine its structure, each rotation smoothing its patterns and guiding its evolution toward the quiet grandeur it displays today. Patterns of motion within the Milky Way do not stay perfectly still. Even though the galaxy appears serene from afar, the stars and gas inside it experience gentle oscillations that ripple through its structure. These movements are subtle, unfolding over millions of years, and arise from the complex gravitational relationships between the disk, the halo, and nearby satellite galaxies. As material orbits the center, it doesn't remain fixed to a single flat plane. Instead, it drifts slightly above and below the galactic midline, creating slow waves that move through the disk like long, rolling undulations. These oscillations add a quiet complexity to the Milky Way's shape, revealing that even a mature galaxy remains responsive to the environment around it. One of the scientific tools used to understand these motions comes from precise measurements of stellar positions and velocities. Modern surveys show that the disk is not perfectly even. It bends and twists in response to gravitational influences. Interactions with the Sagittarius dwarf galaxy, which has passed through the Milky Way's disk multiple times, likely stirred waves of vertical motion that still echo through the stars today. These waves move at different speeds depending on a star's location, creating patterns that astronomers can trace like fingerprints of past encounters. The existence of these ripples suggests that the Milky Way is continually shaped by quiet interactions, each one adding a new layer to its evolving appearance. If you imagine these motions in a more sensory way, they might resemble a slowly breathing sheet of light, rising and falling in gentle arcs as it drifts through space. Stars do not feel this movement individually. Each one follows its orbit as calmly as before, but together they create a collective gesture that adds softness to the galaxy's form. Even the gas in the disk responds to these motions, shifting its density subtly as it passes through regions that are slightly more compressed or slightly more rarefied. These faint adjustments can influence where new stars form, allowing the ripples to shape the galaxy not only through gravitational motion, but through the quiet patterns of light that emerge from young star clusters. In this way, the Milky Way carries its past encounters into its future, letting them echo through its structure with patient, drifting rhythms. Researchers have found additional clues in the chemical makeup of stars across different regions of the disk. Certain populations show distinct metallicity patterns that correspond to waves of star formation triggered by the galaxy's interactions. When a satellite galaxy passes close enough, its gravitational pull can compress gas in the disk, igniting a new generation of stars. These stars preserve the chemical environment of the moment they formed, acting as soft markers that help astronomers reconstruct the timing and nature of the disturbance. By comparing these patterns across the disk, scientists uncover a quiet timeline of subtle interactions, each one leaving behind a gentle imprint on the Milky Way's evolving character. Through all of these motions, the galaxy remains stable, yet never static. Its disk continues to ripple. Its halo continues to interact with neighboring systems, and its spiral arms continue to guide the movement of gas and stars. These long, patient oscillations reveal that even in its calmest eras, the Milky Way is shaped by relationships extending far beyond its own boundaries. The galaxy follows a rhythm that spans billions of years, adapting slowly to each influence while maintaining the gentle structure that has defined it since its earliest days. In these subtle waves and quiet adjustments, the Milky Way carries forward the story of every encounter that helped shape its luminous form. Starlight in the Milky Way has changed many times over the course of its long history, shifting in color, brightness, and distribution as different generations of stars were born and faded. Early on, the galaxy glowed with the light of massive, short-lived blue stars that formed quickly from dense hydrogen clouds. These stars illuminated the surrounding regions with intense brightness, but they exhausted their fuel rapidly, leaving behind heavier elements that enriched the interstellar medium. Over time, the balance of star types shifted towards smaller, longer-lived stars, which now make up the majority of those in the Milky Way. This gradual change in stellar populations created a quieter, more enduring glow, shaping the overall character of the galaxy's light. One of the most insightful scientific findings about the evolution of starlight comes from studying stellar populations known as population 1, 2, and 3 stars. Population 3 stars have never been directly observed, but they are believed to be the first stars that formed after the Big Bang. Massive, metal-free stars that lived short, bright lives. The Milky Way contains no surviving examples of these ancient giants, but it does hold population 2 stars, which formed after the first wave enriched the cosmos with heavier elements. These older stars populate the halo and the thick disk, carrying the chemical signatures of early epochs. The youngest stars, known as population 1, contain the highest levels of heavy elements and form primarily in the spiral arms. This distribution allows astronomers to trace how star formation migrated from ancient, broad regions to the more refined patterns seen today. Picturing these populations together, you might imagine a vast tapestry of colors, each region representing a different moment in the galaxy's quiet evolution. The oldest stars burn with a steady, subdued glow, their long lives unfolding in calm orbits around the center. Younger stars shine more brightly, especially the blue clusters scattered along the spiral arms, where gas continues to collapse into new formations. Dust clouds weave between them like soft veils, shaping the light and adding depth to the Milky Way's glow. Across billions of years, these layers of starlight blend into a gentle radiance that stretches through the disk, illuminated by stars at every stage of their existence. The galaxy becomes a place where time is expressed through light, each generation contributing its own shimmer to the whole. Scientific models of star formation show that the rate at which new stars appear has declined over the galaxy's lifetime. In its youth, the Milky Way formed stars at a much faster pace, fueled by abundant gas and frequent inflows from the cosmic web. As the galaxy matured, its gas supply gradually diminished, and interactions with smaller galaxies became less frequent. Observations indicate that the Milky Way now forms only a few new stars each year, compared to the far more active periods of its early history. This gentle decline reflects the galaxy's transition from a rapidly evolving structure to a more settled one. Even so, pockets of active star formation continue to brighten the spiral arms, ensuring that the Milky Way remains a living, luminous system, not a static relic of the past. Through all of these shifts in starlight, the galaxy has carried forward a quiet record of its own evolution. The mixture of old and young stars, the chemical gradients across the disk, and the distribution of star-forming regions all tell a connected story of change unfolding at a pace almost too slow to perceive. Yet when viewed together, these long cycles reveal how deeply the Milky Way has transformed itself. It has grown from a turbulent sphere of early clusters into a structured, layered spiral, illuminated by stars that reflect every chapter of its history. In this soft glow, the galaxy holds the memory of its long journey, shining gently through the vastness with a light shaped by billions of years of quiet creation. Temperatures across the Milky Way vary in ways that reveal much about the galaxy's structure and history. In the dense central regions, gas can become heated by frequent stellar interactions and by the presence of energetic processes near the supermassive black hole. Farther out, the gas in the spiral arms cools enough for new stars to form, especially in areas where dust and hydrogen clouds gather. The outer disk, with its low-density environment, grows even cooler, allowing delicate filaments of neutral hydrogen to drift for long stretches without collapsing. These temperature differences shape the galaxy's rhythms, determining where stars ignite, where gas settles, and how light travels through the interstellar medium. One of the most useful scientific tools for understanding these variations is spectroscopy, which allows astronomers to analyze the light emitted or absorbed by gases at different temperatures. Hot ionized gas near the galactic center shines brightly in certain wavelengths, while cooler hydrogen clouds in the arms emit faint radio waves detected by large radio telescopes. Observations show that areas with active star formation tend to contain pockets of gas heated by young, massive stars, whose ultraviolet light energizes the surrounding material. In contrast, regions farther from these energetic clusters remain cool, preserving the quiet conditions needed for future star formation. These temperature gradients reveal how energy circulates throughout the Milky Way, influencing the galaxy's structure from its center to its furthest edges. If you imagine these temperature differences as subtle changes in texture rather than warmth, the galaxy might appear as a landscape of gentle contrasts. The central bulge glows with a soft, golden haze shaped by warm, densely packed stars. The spiral arms feel more varied, with bright patches where hot young clusters illuminate the surrounding gas, and darker lanes where cooler dust clouds drift like slow-moving shadows. Between the arms, the gas becomes even more diffuse, creating quiet stretches where starlight filters through without resistance. The outer disk fades into faint, cool regions that lie just inside the halo, where dust thins and the starlight softens into barely visible arcs. These shifts give the Milky Way a layered beauty, shaped not just by motion and gravity, but by the gentle play of temperature across its expanse. Researchers studying the galaxy's thermal structure have uncovered additional insights through observations of the warm ionized medium, a component of the interstellar medium composed of diffuse gas with moderate temperatures. This warm gas forms a kind of gentle backdrop that fills much of the disk, shaped by radiation from older stars and by the remnants of long-past supernovae. Its presence smooths transitions between hotter and cooler regions, allowing energy to spread gradually through the Milky Way. Studies also show that the balance between warm, cold, and hot gas phases influences how efficiently the galaxy forms stars. When too much gas is heated, star formation slows. When enough cool gas collects, new clusters can emerge. These relationships show how sensitively the Milky Way responds to the quiet interplay between temperature and density, allowing the galaxy to regulate its own star-forming activity over immense spans of time. Across billions of years, these thermal patterns have given the Milky Way a gentle self-stability. Hot regions warm their surroundings, cold regions gather the ingredients for new stars, and the warm medium creates smooth transitions that keep the galaxy from shifting too abruptly. Through this balance, the Milky Way has preserved its spiral form while continuing to evolve, letting its luminous patterns reflect the quiet harmony between energy, matter, and motion. The galaxy becomes not simply a structure of stars, but a living canvas shaped by subtle variations in temperature, each one contributing to the soft glow we see stretching across the sky on clear, peaceful nights. Some of the Milky Way's most revealing stories are carried not by stars or gas, but by the dust grains drifting quietly between them. These tiny particles, made of silicates, carbon compounds, and traces of heavier elements, float through the galaxy like soft, dimming veils, absorbing starlight and re-emitting it as gentle infrared glow. Dust may seem insignificant, yet it plays an essential role in shaping the galaxy's appearance and its ability to form new stars. By gathering into dark lanes along the spiral arms, dust outlines the very structure of the Milky Way, tracing curves that become visible even from great distances. Over billions of years, these grains have grown, broken apart, and reformed, becoming subtle markers of the galaxy's changing chemistry. Scientific studies show that dust originates in the outer layers of dying stars, especially red giants and supernovae. When these stars shed their material into space, temperatures drop enough for atoms to bind into microscopic solids. These grains then drift outward, joining the interstellar medium and mixing with gas clouds across the disk. As they accumulate, they influence how clouds cool and collapse, making it easier for stars to form within them. Without dust, hydrogen alone would struggle to dissipate heat efficiently, slowing the entire star formation cycle. The presence of dust therefore accelerates the birth of new stars, even as it obscures them from visible light telescopes. This dual nature, both concealing and enabling, makes dust one of the most quietly influential components of the Milky Way's evolution. To picture dust in the galaxy, you might imagine it as a faint, soft graininess drifting through a beam of light. It gathers in long, delicate filaments that weave between bright clusters, creating pockets of shadow where future stars wait to emerge. Infrared observations penetrate these shadows, revealing warm outlines hidden beneath the dimming effects of dust. The spiral arms, often seen as glowing bands, become more intricate when dust is included in the view. Each curve traced not only by stars, but by the dark lanes that guide gas into gently collapsing knots. Dust adds a sense of depth and layering to the Milky Way, giving it a textured presence that changes subtly as the galaxy rotates. Researchers examining the chemical composition of dust have discovered that its makeup varies across different regions of the galaxy. Closer to the center, dust contains higher concentrations of heavy elements, reflecting the more rapid star formation and enrichment that occurred there. In the outer disk, where star formation happens more slowly, dust grains tend to be simpler and smaller, shaped by a less chemically diverse environment. These patterns help astronomers map the life cycle of matter within the Milky Way, revealing how each generation of stars contributes to the ingredients needed for the next. Even the size of dust grains provides clues. Larger grains often form in dense environments, while smaller ones dominate regions where radiation gradually erodes their surfaces. These variations turn dust into a quiet record of where the galaxy has been most active and where it has evolved more gently. Across immense spans of time, dust has helped sculpt the Milky Way's structure, influencing everything from the cooling of gas to the formation of planets around young stars. It thickens in some regions, thins in others, and continually cycles between clouds and starlight, shaping the galaxy with a softness that belies its significance. Through its subtle presence, dust demonstrates how even the smallest components of the cosmos can guide the evolution of vast structures. In the Milky Way, these drifting grains form a quiet, unbroken thread, connecting old stars to new, carrying the galaxy's long story across time with delicate persistence. One of the most intricate aspects of the Milky Way's evolution lies in the way gas cycles through the galaxy, moving from one phase of existence to another as it travels between stars. Gas does not remain fixed. It flows, cools, heats, and circulates in long, quiet loops, driven by gravity, radiation, and the explosive energy of dying stars. These cycles create a balance between creation and dispersion, allowing the galaxy to form stars steadily over billions of years without exhausting its supply of material. Each pocket of gas carries the potential to become something new, and the way it moves through the Milky Way helps set the pace of the galaxy's ongoing transformation. One of the fundamental scientific insights into this process involves the interplay between stellar winds, supernova explosions, and the large-scale motions of the interstellar medium. When massive stars reach the end of their lives, they release energy that pushes surrounding gas outward, creating bubbles and cavities within the disk. These expanding shells can merge and overlap, forming superbubbles that stretch for hundreds of light years. As they grow, they can lift gas out of the disk and into the lower halo, where it cools and eventually falls back toward the galaxy. This creates a gentle fountain-like circulation, with material rising and settling over vast timescales. Astronomers believe this circulation helps regulate the Milky Way's star formation by redistributing gas from crowded regions to quieter ones, maintaining a soft equilibrium across the disk. You might imagine these motions not as forceful eruptions, but as broad, slow currents drifting upward before sinking back into the spiral arms. The gas rising into the halo glows faintly in ultraviolet light, warmed by the radiation of nearby stars, while the material descending toward the disk cools and thickens into clouds that can someday form new stars. Over millions of years, these motions blur the boundaries between the disk and halo, creating a transitional region filled with warm gas that flows with a subdued, almost tidal rhythm. The galaxy's shape appears solid when viewed from afar, yet internally it behaves like a system in constant circulation, quietly shifting its material among different layers. Scientific studies of this cycling process also reveal the importance of molecular clouds, the dense, cold regions where stars are born. These clouds form when gas cools enough to bind into molecular hydrogen, a process made easier by the presence of dust that shields the molecules from disruptive radiation. Molecular clouds often emerge in the spiral arms, where density waves compress gas into thicker lanes. Inside these clouds, gravity slowly gathers material into clumps, eventually triggering the birth of new stars. But these same stars send out radiation and winds that erode the clouds from within, dispersing much of the material back into the interstellar medium. This feedback loop ensures that star formation does not progress too quickly, preserving the galaxy's balance and shaping the rhythm of new starlight across the disk. Over long stretches of time, these gas cycles help define the Milky Way's character. Hot gas rises, cool gas settles, clouds form and dissolve, and new stars emerge only to later return their enriched material to the galaxy. This slow, repeating exchange has allowed the Milky Way to sustain billions of years of star formation, while gradually building the chemical diversity needed for planets, atmospheres, and eventually life. Through the quiet circulation of its gas, the galaxy renews itself again and again, carrying forward the elements of earlier generations while shaping the conditions for futures yet to unfold. In this delicate balance, the Milky Way expresses one of its most enduring qualities: its ability to evolve gently, with each cycle contributing to the soft glow that fills its spiral arms. Every galaxy carries a trace of the larger cosmic landscape it inhabits, and the Milky Way is no exception. Long before it developed its elegant spiral form, it was shaped by its place within the vast network of filaments and voids that make up the universe's large-scale structure. These filaments, immense, thread-like formations composed of gas, stars, and dark matter, acted as highways along which material drifted toward emerging galaxies. The Milky Way grew at the intersection of several of these cosmic streams, receiving a steady inflow of hydrogen and small satellite galaxies that helped guide its early evolution. Even today, the galaxy's motion through the cosmos reflects these ancient connections, carrying faint echoes of the forces that shaped its earliest form. One of the clearest scientific insights into this larger context comes from observing how galaxies cluster together in groups. The Milky Way is part of the local group, a collection of more than 50 galaxies bound together by gravity. The two largest members, our galaxy and the Andromeda galaxy, dominate the group, while smaller galaxies orbit both as satellites. These companions are not static. They interact with the gravitational fields of the larger galaxies, influencing the motions of stars and gas along their outer edges. Scientists believe that the Milky Way's position within the local group helped determine how it accreted material during its youth. Filaments feeding into this region of space funneled gas toward the galaxy, allowing it to grow steadily over billions of years, while small galaxies drifting through the group occasionally merged with it, adding new stars to the halo. If you picture the local group from a quiet distance, it might resemble a loosely scattered cluster of lanterns floating in an immense expanse. Each galaxy glows with its own character, yet all are drawn into slow mutual orbits around a shared gravitational center. Between them stretches a thin medium of gas and dark matter, forming subtle bridges that guide their long-term evolution. The Milky Way and Andromeda drift toward one another at hundreds of kilometers per second, though the distance between them is so great that their inevitable meeting remains billions of years away. In this slow drift, the local group becomes not just a collection of galaxies, but a shared environment where each member's gravity contributes to the overall structure, shaping motions that unfold across cosmic time. Researchers studying the distribution of dark matter in the local group have uncovered evidence that the Milky Way sits within an extended dark matter halo far larger than the galaxy itself. This halo interacts with Andromeda's, forming a massive overlapping region of gravitational influence. Simulations suggest that this shared envelope guides the long-term motions of both galaxies, drawing them slowly toward one another. The presence of this dark matter connection helps explain the relative velocities of many smaller satellite galaxies, whose paths align with the predicted gravitational landscape. Observations of distant galaxy groups show similar patterns, reinforcing the idea that galaxies rarely evolve in isolation. Instead, they grow within communities shaped by surrounding halos and filaments, each contributing to the overall dynamics of the group. Across billions of years, the Milky Way's interactions within the local group have helped refine its structure. Small galaxies drawn too close were gradually pulled apart, their stars stretched into arcs that now drift through the halo. Streams of gas moved along the cosmic filaments, feeding star formation in the disk and helping sustain the spiral arms. Meanwhile, the gravitational pull between the Milky Way and Andromeda subtly influenced the outermost regions of both galaxies, shaping their long-term paths even from vast distances. Through these relationships, the Milky Way became part of a larger tapestry, one where galaxies guide and respond to one another with slow, enduring motions. The galaxy we know today carries the imprint of these connections, shaped not only by its internal processes, but by the quiet influence of its companions drifting through the same cosmic neighborhood. Among the subtler forces shaping the Milky Way is the steady pull of gravity acting on stars over long stretches of time, guiding them into patterns that reveal the galaxy's deeper structure. Even a single star carries information about the gravitational landscape it moves through, tracing an orbit that reflects not only the visible matter around it, but the unseen distribution of dark matter as well. By studying these stellar motions, astronomers can reconstruct the outline of the galaxy's hidden mass, uncovering how the Milky Way holds itself together. This quiet, continuous choreography has unfolded for billions of years, shaping the galaxy's form with a gentle but persistent influence. A major scientific insight into the Milky Way's mass distribution comes from mapping the orbits of stars at different distances from the center. Observations show that stars far out in the disk orbit the galaxy at nearly the same speed as those much closer in. If only visible matter were present, these outer stars would move far more slowly, unable to hold their paths against the pull of gravity. The fact that they do maintain these high velocities provides strong evidence for the vast halo of dark matter enveloping the Milky Way. This halo extends far beyond the visible disk, forming an enormous, diffuse sphere of invisible mass that shapes the galaxy's rotation and stabilizes its structure. Without it, the spiral arms would not remain as coherent as they are, and the disk would likely have thinned or dispersed long ago. To imagine how stars move through this gravitational environment, you might picture them as quiet travelers following gentle, looping paths through a lantern-lit valley. Each orbit reflects a delicate balance between the star's own momentum and the pull of the galaxy's combined mass. Some stars glide along nearly circular paths within the thin disk, while others rise above and below the plane in smooth arcs, shaped by interactions with spiral arms or past encounters with small galaxies. Halo stars move with even more freedom, tracing elongated orbits that carry them through regions where starlight thins and darkness grows. Their motions reveal the Milky Way's three-dimensional shape, showing how the galaxy extends far beyond the bright band visible on a clear night. Scientific models that incorporate these stellar motions have shown that the Milky Way's dark matter halo is not perfectly spherical. Instead, it appears slightly flattened or elongated in certain directions, possibly influenced by interactions with the Large Magellanic Cloud or other satellites. Recent measurements suggest that the halo itself may be moving, its center of mass shifted subtly by the gravitational tug of nearby galaxies. These discoveries highlight the Milky Way's dynamic nature, showing that even its unseen components respond to the slow, ongoing changes in its cosmic environment. Dark matter may be invisible, but its influence shapes everything from the rotation of the spiral arms to the formation of streams and shells in the halo. Over long periods of time, the combined motions of millions of stars create a kind of quiet harmony, revealing the balance of forces that hold the Milky Way together. The disk rotates as a unified structure, supported by the halo's gravitational embrace. The bar channels stars inward and outward, adjusting their paths like a gentle stirring motion. The spiral arms guide gas into new clusters, which then join the dance with their own orbits. Through all of this, the stars record the galaxy's past interactions and its internal shifts, preserving these memories in the shapes of their paths. In their motion, the Milky Way expresses both its history and its present, carrying the influence of dark matter, cosmic flows, and ancient mergers in every gentle turn across its luminous expanse. The Milky Way's long history is also written in the ages of its stars, each one a quiet marker of when and where it formed. By examining these ages, astronomers can reconstruct the sequence of events that shape the galaxy, tracing how star formation moved from the inner regions to the outer disk, and how mergers influenced different stellar populations. This chronology reveals a galaxy that did not grow uniformly, but evolved through waves of activity, some intense and brief, others extended and gentle. Across billions of years, these patterns created layers of starlight that now coexist in the spiral arms, the bar, the bulge, and the halo, each region holding its own chapter of the Milky Way story. One of the most important scientific tools in this work is asteroseismology, the study of oscillations within stars. These vibrations cause subtle changes in brightness that vary depending on the star's internal structure, which in turn evolves as the star ages. By measuring these oscillations, astronomers can estimate a star's age with remarkable precision, revealing not only when it formed, but also how its birth environment influenced the larger galaxy. Studies using data from space telescopes have shown that the inner disk contains many older stars, suggesting that star formation began vigorously near the center before gradually spreading outward. Meanwhile, the outer disk hosts younger populations formed from gas that arrived later, carried by cosmic filaments or stirred by past encounters with smaller galaxies. You might imagine these age differences as quiet shades of color cast across the galaxy. The central bulge glows with the warm tones of old stars whose light has softened over billions of years. The thick disk carries a mixture of hues shaped by ancient bursts of star formation and by stars that migrated from other regions. In the thin disk and spiral arms, younger stars brighten the scene with cooler, more energetic light, especially in regions where clusters have recently formed from dense molecular clouds. Together, these populations form a layered luminosity, where age becomes a soft gradient spreading outward from the core. The Milky Way's appearance is therefore not just a reflection of where stars are located, but of when they came into existence and how they have moved since that moment. Scientific analyses of stellar ages reveal additional clues about the galaxy's mergers. Certain populations of stars in the halo and thick disk show ages and chemical signatures consistent with having originated in smaller galaxies that merged with the Milky Way long ago. These stars often follow eccentric or inclined orbits, preserving the dynamics of the systems they once belonged to. By comparing age distributions across these regions, astronomers can identify distinct merger events and estimate when they occurred. One such event, known as the Gaia-Sausage-Enceladus merger, likely took place around 10 billion years ago, profoundly reshaping the early Milky Way and contributing many of the stars now residing in the halo. These findings highlight how age functions as a quiet archival tool, preserving the memory of interactions long after the galaxies involved have disappeared into the larger structure. Over immense stretches of time, the shifting patterns of star formation gave the Milky Way a complex yet harmonious composition. Old stars continued to drift through the halo and bulge, while younger ones brightened the spiral arms and thin disk. Intermediate-age stars filled the spaces between, linking different eras of the galaxy's evolution. This layered arrangement created a sense of continuity across billions of years, allowing every generation of starlight to contribute to the luminous form we see today. Through the ages encoded in its stars, the Milky Way carries the imprint of its entire journey, from its chaotic beginnings to the elegant spiral structure it eventually developed, holding its long past with a softness shaped by gravity, time, and the quiet cycles of creation. The satellites that accompany the Milky Way offer another window into its history and future, orbiting like quiet companions that have shaped the galaxy in ways both subtle and lasting. These smaller galaxies move through the Milky Way's outer halo, bound by gravity, yet following paths that can shift over billions of years. Each one carries a distinct population of stars, chemical signatures, and motions that reflect its origin. Some have remained with the Milky Way for a long time, while others appear to be newcomers drawn inward by the galaxy's gravitational pull. Together, they form a constellation of faint structures that interact gently with the larger spiral, guiding parts of its evolution from the outskirts. Two of the most influential satellites are the Large and Small Magellanic Clouds, irregular galaxies that orbit the Milky Way in a loose dance. Scientific measurements show that the Magellanic Clouds are moving rapidly along their current trajectories, likely not long-term stable satellites, but visitors captured relatively recently on cosmological timescales. Their rapid motion and considerable mass exert a noticeable pull on the Milky Way, subtly shifting its center of mass and stirring the outer regions of its dark matter halo. Simulations suggest that their presence may even contribute to the warp observed in the Milky Way's outer disk, a ripple-like deformation that extends across vast distances. These findings reveal that even distant companions can influence the structure of a galaxy as large as our own, shaping its form through quiet gravitational exchanges. Imagining the Magellanic Clouds from the Milky Way's perspective, one might see them as drifting clusters of pale starlight, tracing broad arcs across the outer halo. Streams of gas trail behind them, forming the Magellanic Stream, a long ribbon of hydrogen stretching nearly halfway around the sky. This stream, drawn out by gravitational tides and ram pressure interactions, provides a living record of the past encounters between the clouds and the Milky Way. As the gas gradually falls toward the galaxy, it may someday fuel new star formation in the outer disk, linking the fates of these companion galaxies and the Milky Way in a slow, ongoing exchange. Their motions show how galaxies can shape one another without ever colliding, simply through the persistent influence of gravity working over enormous timescales. Researchers studying the Milky Way's satellite system have also found evidence for many faint dwarf galaxies that orbit farther out. Some of these dwarfs contain only a few thousand stars, yet their motions reveal the presence of dark matter, making them some of the most dark matter-dominated systems known. Their orbits help trace the shape of the Milky Way's gravitational field, offering clues about the distribution of dark matter in the outer halo. Many of these dwarfs appear to have arrived in small groups, rather than individually, suggesting that the Milky Way accretes satellites in clusters, much as it accretes gas along cosmic filaments. These discoveries highlight the layered structure of the galaxy's surroundings, where satellites continually arrive, evolve, and sometimes dissolve into streams that wrap around the halo. Over time, the gravitational pull of the Milky Way will continue to guide these satellites along new paths. Some will be drawn closer, losing stars to tidal forces that stretch them into elongated trails. Others will remain in stable orbits for billions of years, slowly shaping the outer halo while preserving pieces of their independent histories. The Magellanic Clouds will eventually settle into more regular orbits or merge with the Milky Way altogether, contributing their stars and gas to the galaxy's continued evolution. Through these ongoing interactions, the Milky Way is reminded that it is part of a broader community, a cluster of galaxies sharing a region of space and influencing one another in subtle, gentle ways. In the long arc of time, these companions help shape the galaxy's future, adding new layers to its story with each slow orbit across the darkness. Not every part of the Milky Way shines with the same brightness. Some regions glow intensely with newborn stars, while others remain dim, filled with cold gas and quiet lanes of dust that have not yet condensed into new light. These contrasts reveal how unevenly the galaxy evolves across its vast disk. Star formation tends to occur in bursts, concentrated in certain environments where conditions allow gas to cool and collapse efficiently. Other regions drift through long periods of stillness, with gas too diffuse to gather and form clusters. The patchwork of active and inactive zones gives the Milky Way a textured rhythm, as if different areas are resting while others are just beginning to awaken into starlight. One of the central scientific tools for studying these differences is the observation of giant molecular clouds, enormous structures containing the coldest, densest gas in the galaxy. These clouds are the birthplaces of stars, often spanning dozens or hundreds of light years. Inside them, gravity slowly gathers material into clumps that can form star clusters. But molecular clouds do not appear everywhere. They tend to form in the spiral arms, where density waves compress gas into thicker lanes, or in the aftermath of interactions with satellite galaxies that stir the disk. Regions between the arms, known as interarm areas, contain less dense gas, making star formation rarer. By mapping the distribution of these clouds, astronomers can trace where the Milky Way is most actively creating new stars and where it has entered quieter phases of evolution. If you imagine the galaxy from above, this distribution might resemble a slowly swirling mosaic. Bright knots of newborn stars highlight the spiral arms like scattered lanterns, while the darker gaps between them hold vast stretches of undeveloped potential. Dusty lanes run along the arms, dimming the light behind them and adding depth to the galaxy's appearance. In some areas, clusters shine together in soft bluish hues, marking places where hot, young stars have recently emerged. In others, older populations glow more evenly, creating smooth fields of warm starlight that hint at earlier epochs of activity. This interplay gives the Milky Way a layered texture, shaped by regions lighting up and fading at their own pace, each one following the local conditions that govern gas, dust, and gravity. Scientific analyses reveal additional patterns in the Milky Way's star-forming regions. One important discovery is that metallicity, the abundance of elements heavier than helium, plays a key role in determining how effectively gas can cool. Areas with higher metallicity radiate heat more efficiently, allowing gas clouds to collapse more easily and form stars. This is why the inner disk, enriched by countless cycles of star formation, tends to produce stars more readily than the outer regions, where the chemical composition reflects fewer generations of enrichment. Observations of external galaxies show similar gradients, suggesting that this pattern is a natural part of spiral galaxy evolution. The Milky Way's metallicity gradient therefore acts as a quiet record of its star-forming past, influencing the pace at which future stars will appear. Over billions of years, the uneven distribution of star formation has helped shape the Milky Way structure. Some spiral arms appear more prominent because they contain more active regions, while others seem softer or more diffuse. The central bar channels gas toward the inner disk, creating bright concentrations of star formation near the core, while the outskirts remain calm, slowly gathering the gas that will feed future generations of stars. This balance between activity and quiet ensures that the Milky Way continues to evolve gradually, sustaining its form without exhausting its resources all at once. Through this mosaic of bright and dim regions, the galaxy reveals its long, patient cycles, patterns of creation and rest unfolding gently across the luminous sweep of the spiral arms. Across the Milky Way, magnetic fields thread through the galaxy like invisible lines of tension, guiding the movement of charged particles and subtly shaping the behavior of gas and dust. Though these fields are far too weak to influence the orbits of stars, they play a significant role in the finer details of the interstellar medium, affecting how clouds collapse, how cosmic rays travel, and how certain structures within the spiral arms take shape. They extend through the disk and halo, forming patterns that can twist, bend, and stretch over vast distances. For something so faint, these fields leave a surprisingly noticeable imprint on the Milky Way's evolution, influencing processes that unfold quietly, far below the brightness of starlight. One key scientific discovery is that the Milky Way's magnetic field is organized on both large and small scales. On the scale of the entire disk, the field follows the spiral pattern of the galaxy, aligning with the broad sweep of the arms. Closer in, the field becomes tangled and irregular within molecular clouds, where turbulence and star formation distort the lines. Observations using polarized radio waves reveal these patterns, allowing astronomers to map the geometry of the field and understand how it interacts with interstellar gas. Studies show that magnetic fields help support clouds against collapse, countering gravity just enough to slow the formation of stars. This balance shapes how quickly the Milky Way forms new clusters, subtly regulating the pace of its ongoing evolution. Imagining these fields requires translating something invisible into a quiet sense of motion. You might picture faint strands stretched through the disk, forming gentle arcs that flow alongside the spiral arms. Charged particles drift along these lines, tracing them like soft filaments of light that bend around clouds and curve through regions of warm gas. Where the field becomes tangled, the motions resemble slowly swirling knots, dense, dim spaces where dust gathers and where future stars may eventually emerge. In the darkest regions, the magnetic field shapes the thin, thread-like filaments found within molecular clouds, guiding the paths along which gas collects before forming stars. These delicate interactions give the galaxy a hidden structure, one that adds subtle guidance beneath the broader motions of rotation and gravity. Researchers studying the Milky Way's halo have discovered that magnetic fields extend far beyond the disk, filling a wide region of hot, diffuse gas that surrounds the galaxy. This halo field appears to be shaped by outflows from the disk, including the remnants of ancient star-forming events that pushed gas upward and carried magnetic energy with it. Observations of radio emissions from the halo suggest that these magnetic structures can influence how cosmic rays propagate through the galaxy, directing their motion along long arcs that stretch thousands of light years. The presence of magnetized outflows also hints at a dynamic past, where powerful events near the center, or in the star-forming regions of the inner disk, sent gas and magnetic energy cascading into the surrounding space. Even now, these faint structures continue to interact with the outer halo, creating a quiet conversation between the disk and the space beyond. Over billions of years, the Milky Way's magnetic fields have acted as a kind of subtle architecture, shaping the smallest details of the galaxy's evolution. They influence how clouds collapse, how dust aligns, how cosmic rays travel, and how gas circulates within and beyond the spiral arms. Though they do not define the galaxy's global structure, they add depth and texture to its internal motions, guiding processes that unfold far below the brightness of stars. In these faint, invisible lines, the Milky Way reveals yet another layer of complexity, one that weaves through the galaxy with delicate persistence, shaping its quiet rhythms across time and giving the interstellar medium a hidden, ever-shifting form that mirrors the softness of its luminous spiral. The shape of the Milky Way is not perfectly fixed. It bends and stretches in ways that reflect its long history of interactions and internal motions. Even though we often picture the galaxy as a flat, symmetrical disk, careful observations reveal that the outer regions curve upward on one side and downward on the other, creating a gentle warp that spans tens of thousands of light years. This warp shifts slowly over time, guided by the gravitational influences of nearby galaxies and by the distribution of dark matter in the halo. Rather than being a rigid structure, the disk behaves more like a flexible sheet, responding to subtle forces. These quiet distortions help astronomers understand how the Milky Way exchanges momentum with its surroundings and how its outer layers evolve across vast stretches of time. One of the most informative scientific discoveries in this area comes from mapping the motions of hydrogen gas in the outer disk. Radio observations show that the warp follows a predictable curve, rising above the plane of the inner disk before dipping below it on the opposite side. The pattern is consistent with models in which the gravitational pull of the Large Magellanic Cloud or other nearby satellites tugs on the Milky Way's outer regions. Surprisingly, measurements suggest that the warp itself rotates slowly, completing a turn over several 100 million years. This motion indicates that the warp is not a relic of a past event, but a feature continually shaped by the present gravitational environment. Its rotation adds another layer of subtle motion to the galaxy, revealing that even the outermost regions respond to forces acting far beyond the visible disk. If you imagine this warp visually, it might resemble a wide ribbon gently twisting as it drifts through a calm breeze. Stars and gas follow these curves without friction or pressure, simply responding to the gravitational landscape around them. The spiral arms extend gracefully into the warped regions, their luminous patterns bending slightly as they trace the curvature of the disk. In some areas, dust lanes follow these arcs, adding depth and dimensionality to the shape. The warp gives the galaxy a three-dimensional presence, reminding us that the Milky Way is not a flat painting in the sky, but a living structure shaped by motion, gravity, and the long memory of past encounters. This subtle bending becomes part of the galaxy's larger story, reflecting influences that remain invisible without careful measurement. Researchers studying the stars in the warped regions have uncovered additional insights into its origins. Some stars in these outer areas follow orbits that differ slightly from those in the inner disk, suggesting that the warp may be connected not only to satellite interactions, but also to internal processes such as the misalignment between the disk and the dark matter halo. If the halo is tilted or elongated, it can create a torque on the disk, gradually altering its shape. Models also show that inflowing gas from the cosmic web may arrive at angles that do not perfectly match the plane of the disk, adding material that reinforces the warp over time. These findings highlight the layered nature of the phenomenon, showing that the warp emerges from multiple influences rather than a single event, becoming a quiet record of the galaxy's relationship with its environment. Over billions of years, the warp has become a defining feature of the Milky Way's outer structure. It changes slowly but persistently, shifting in response to the orbits of satellite galaxies, the flow of intergalactic gas, and the subtle contours of the surrounding dark matter halo. Far from being a sign of instability, the warp demonstrates the galaxy's flexibility, its ability to adapt to external forces while maintaining its spiral shape. In this gentle bending, the Milky Way reveals another aspect of its long evolution, showing how its form continues to respond to distant companions and invisible structures. The warp becomes a quiet expression of the galaxy's connection to the larger cosmos, curving softly as it drifts through time and space with the graceful patience that has defined its history from the beginning. The edges of the Milky Way blend gradually into a region known as the circumgalactic medium, a vast reservoir of diffuse gas that surrounds the galaxy far beyond its visible disk. This enormous, gently glowing halo contains material that has been cycling in and out of the Milky Way since its earliest days, carrying with it the chemical signatures of ancient generations of stars. Though faint and difficult to observe directly, the circumgalactic medium plays a vital role in regulating the galaxy's evolution. It acts as both a source and a sink for gas, providing material that can eventually cool and fall back into the disk, while also absorbing the remnants of past star formation and energetic outflows. In this quiet envelope, the Milky Way interacts with the broader intergalactic environment, exchanging matter in ways that unfold softly across billions of years. Scientific observations using ultraviolet spectroscopy have revealed that the circumgalactic medium contains multiple layers of gas at different temperatures. Some of this gas is warm and ionized, glowing faintly under the influence of starlight and cosmic radiation. Other portions are much hotter, reaching millions of degrees and emitting X-rays detectable by orbiting telescopes. This hot gas likely originates from ancient supernova explosions and outflows driven by periods of intense star formation near the galactic center. Meanwhile, cooler gas may come from infalling streams drawn along cosmic filaments or from satellite galaxies interacting with the Milky Way's halo. These distinct components show that the circumgalactic medium is not a uniform cloud, but a dynamic, evolving system shaped by a mixture of internal and external processes. To imagine this region, one might think of a soft, luminous mist encircling the galaxy, extending so far that it dwarfs the visible spiral arms. Stars do not shine brightly here, yet their influence reaches outward through radiation, gravity, and the faint pressure of stellar winds. The gas in the circumgalactic medium moves slowly, drifting in gentle flows that respond to the contours of the dark matter halo. Some streams fall inward toward the disk, cooling as they descend, while others rise outward, heated by the energy released from clusters of young, massive stars. These motions form a delicate circulation, a quiet exchange that connects the Milky Way to the larger structures around it. Through this halo, the galaxy breathes, drawing in new material while releasing the remnants of older generations. Researchers studying this region have found that the circumgalactic medium contains far more mass than the gas found within the disk itself. This discovery helps solve a long-standing scientific question known as the missing baryon problem, which refers to the discrepancy between the amount of ordinary matter predicted by cosmological models and the amount observed within galaxies. Much of the Milky Way's baryonic matter appears to reside in this extended halo, hidden from view except in ultraviolet absorption lines and faint X-ray emissions. The presence of these missing baryons helps explain how the galaxy has sustained star formation for such a long time, providing a reservoir that replenishes the disk when conditions allow. It also shows that galaxies are not isolated islands of stars, but are deeply connected to vast structures of gas that stretch across intergalactic space. Over the course of billions of years, the circumgalactic medium has shaped and been shaped by the Milky Way's evolution. Gas expelled during ancient bursts of activity now floats quietly in the halo, slowly cooling until it may one day return to the disk. Infalling material from cosmic filaments provides fresh fuel for star formation, ensuring that the spiral arms continue to brighten with new clusters. Interactions with satellite galaxies stir the halo, creating subtle flows and eddies that echo the motions of the larger galaxy. Through this gentle exchange, the circumgalactic medium becomes both a record of the Milky Way's past and a reservoir for its future, sustaining the slow, luminous unfolding of its long cosmic story. As our quiet journey through the beginnings of the Milky Way comes to a close, the galaxy settles once more into a soft sweep of starlight stretching across the dark. Every layer of its history, from ancient clouds of hydrogen to the slow drift of satellite galaxies, adds its own faint shimmer to the night sky. What began as scattered gas in the early universe became a vast spiral of stars, dust, and gentle motion, shaped by time so long and patient it almost feels still. Letting these stories fade into the background now, you can imagine the galaxy resting in its slow rotation, carrying billions of stars through the calm of interstellar space. Thank you for spending this time here, exploring these quiet origins and distant epochs. There is always more to discover, yet nothing demands attention in this moment. You can let the last details drift away, knowing the Milky Way continues its long journey far beyond the reach of thought or sound. As the light grows softer and the rhythms slow, may the calm of the cosmos stay with you for the rest of the night.